Well, welcome and thank you for coming to the first talk. No, but to the organizers, I'm really delighted to be here and looking forward to sharing some material with you. And Jim handed me my... I
guess you don't need this.
Yes. Jim handed me my first joke, which is, I wasn't really sure what to speak on for this, and so I chose two pretty unrelated things that I thought would have different appeal to different people. And it turns out that there's a common thread through it, so I'm going to kind of give an overview, which is much broader, and then show where these two pieces of work fit in. And the theme that I'll be kind of tying everything together with are these monotone surfaces. So if you think of it, I'm on either the 2- or 3-dimensional lattice here, and I have squares or cubes that are all supported on their underside. And so this is quite familiar. This is just a monotonic lattice path. Okay, so this is what I'll call the 1-dimensional version. And, I'm sorry, I'm actually calling this the 2-dimensional version, but it's a 1-dimensional path. And this is lozenge tiling. So if you haven't seen it before, I really intend it as a 2-dimensional picture, which you could think of as the surface of a bunch of little boxes. And again, it's monotonic, that if something is there, everything underneath it in all 3 directions is also there. And of course, it looks like a 3-dimensional surface, so this will be my 3-dimensional monotonic surface. The top envelope is the lozenge tiling I'll be talking about. And obviously, I could generalize this to higher dimensions. So these structures come up surprisingly often across problems. So the path, which I'll spend the first half of the talk talking about, no, it's not really the first half, but it's the first part. It comes up in exclusion processes, permutations, and integer partitions. And if that doesn't make sense to you, I'm going to show you in half a second. And the surfaces, I said already, were lozenge tilings. The shapes are like plane partitions, where you could think of the height of each column being a number, and these are decreasing or as you go across or down. And it's also a dimer model on the dual hexagonal lattice. So you could think of each lozenge as gluing together 2 adjacent triangles, which is equivalent to a perfect matching on the dual graph, which is the hexagonal lattice. So there's a lot of things in mind. So let me just talk about the one-path model. So I have one path. I've rotated it by 45 degrees. And now I could think of it as mountains and valleys. And I can do a move where I invert something and make it into a peak or a valley locally. This is a Markov chain that we're going to be talking about throughout the talk. And I can view this as an exclusion process on the line, where if I go up, I have a particle, and if I go down, I have an empty space. And this mountain-valley move is precisely moving one particle to the right or to the left, okay? So this is a very simple process. It comes up in permutations. If you're doing nearest neighbor permutation, so you choose 2 adjacent numbers in a permutation and switch them, you could decompose it into a set of these 0, 1 paths where each one is a threshold function. It's 1 if the number is higher or lower than something. So I have the threshold functions from 1 to 6 on the right. And when I do this nearest neighbor transposition, I'm just doing exactly the 0, 1 switching that I talked about a second ago. And the last one, which is one of the problems that I'll be spending a lot of time on today, is integer partitions. So integer partitions are, I take an integer and I break it into some number of integral parts, and I sort them in order. The order of the pieces doesn't matter, so I might as well sort them. So I have, at the bottom, 3 different partitions of 11. One of them is just 11, and then the other 2, 5, 3, 3, 5, 4, 1, 1. If I sort, I'm representing this as a lattice path. And what they have in common, these are the Ferrer's diagrams of integer partitions. So all of the partitions of 6 are in this yellow rectangle, and they're all they're all of these monotonic paths with exactly area 6 underneath. Okay, so this captures what I'm going to try to sample later. So my sampling question is, can we sample partitions of n uniformly by an efficient algorithm? And a Markov chain is certainly a good candidate. And so I want something that my output always has area n, and all things are equally likely or close to equally likely. Okay. This is just the preamble to show you a bunch of problems that all have a commonality. So we talked about the paths. We talked about these lozenge tilings, which again is a two-dimensional model with a three-dimensional, well, I'm sorry, it's a two-dimensional model with a three-dimensional box representation. And I'm going to be more interested in capturing it as disjoint paths. Okay? So I'm on a rotated lattice. My paths go up or down, and they're vertex disjoint. So they're completely disjoint paths. And if I had a bounding region, and I told you where the starting points and ending points, there's a perfect bijection between lozenge tilings and these lattice paths, which hopefully you can believe. If you look at it, it's just the level sets. Okay? So if you look at it in the right orientation, these are just capturing what you have on each of the different rows. Okay? You could also consider a similar lattice path model, which will bring me to the second part of my talk, which is I could consider paths that are edge disjoint but can share a vertex. Okay, so this, I'm rotating back to the axis aligned orientation. And here you could see, I could think of these as crossing paths. I'm going to choose to interpret each intersection so that I have one path above another path, and they're edge disjoint, but they can share vertices. All right? So this might seem a little arbitrary, but I'm going to fix a color in the lower left corner. Notice that the color, oh, sorry, I'm giving it away. So I'm going to use the following rule. So every time I cross a thick blue bar to the right, I'm going to go up by 1 mod 3. And every time I cross a thin bar, I'm going to go down by 1 mod 3. And then I have a similar rule as I go horizontally. It turns out these rules are well defined. They translate, they extend from 0, and you get a complete picture like this, and you will get a proper 3 coloring. And this is, again, a bijection. So I could capture, if I'm interested in the set of 3 colorings of the lattice, I can capture this by a set of edge disjoint lattice paths on the grid. So it's pretty cool that you have these 3 very different problems that come up. So this is the plan for my talk. I am going to first talk about, for these, the lozenge tiling model and the path model, how you sample in the unweighted case. So the most natural setting where all colorings, all lozenges, all have equal weight, and I want to sample one uniformly. The second part, I'm going to talk about biased surfaces. So I'm going to bias and favor things with large or small area underneath, okay? And we saw something a second ago about a demonstration tomorrow on Boltzmann samplers, and this is going to come up in the strategy that I use here. So mainly this part of the talk I'll apply to integer partitions. And then the third part of the talk, I'm going to talk about sampling weighted surfaces. So weighted and biased are slightly different. Biased is I'm biasing to adding more cubes or more squares. Weighted is going to be a product measure, and it's going to be a local function, which I'll explain. And it's a natural generalization of 3 colorings, which is called the 6 vertex model. Okay, so that's quite a lot, and that will be the second half of my talk, but that's what I'm going to try to go through. Okay, so starting with the unweighted case, I guess as warm-up, I have a lattice path, and I'm going to look for a way to sample from the 2n choose n possible lattice paths that start at one corner and end at the other corner of an n by n region. Yeah? Okay. So here's one. And my Markov chain is going to choose a point along this lattice path by dropping a vertical. It intersects this once. And if it's a peak, then I could invert it and map it to a valley. And this is invertible. So on the right, if I chose this point, I could go back. I'm going to demonstrate that in a second, but this is the algorithm, is I drop a vertical line uniformly from left to right. If it's a peak, I'm going to flip it down to a valley with probability 1/2 and keep it where it is with 1/2. And if it was a valley, I'll flip it back or keep it the same. Okay, very simple. So this is a reversible Markov chain. If I can go from A to B, I could go from B back to A. So I can do that by pushing that point up. It's ergodic. I could get to everything. I could always get down to the lowest surface or lowest path. So I connect everything. And the question I'll be asking throughout the talk is how long? How long does it take if I start at a particular place to converge to close to the uniform distribution? Okay. So the measure that we use for this is the mixing time, which is when the total variation distance between your current distribution after evolving the Markov chain for a certain number of steps and your stationary distribution, which you will eventually converge to, when the L1 distance is twice epsilon. Okay, so the variation distance is how much one distribution is above the other, which is half of the unsigned difference between the probabilities at all of the different points, which I tried to demonstrate with this picture that my student said doesn't work, but I left it in. And okay, so the mixing time, once you get within epsilon, you'll stay within epsilon after that. Okay, so this is going to be decreasing. And I'm using the computer science terms that a Markov chain is rapidly mixing or polynomially mixing. If starting at my initial configuration, after polynomial time, I'm within epsilon of the goal stationary distribution that I'll eventually approach, okay? And I say that it's slowly mixing if that takes exponential time. Okay, so those are the terms, and throughout the talk, I'll be distinguishing when it's fast and when it's slow.
You should use tractable and intractable.
But I'm going to be showing you n to the 16th algorithm, so you might not want to use that. Okay. So David Wilson gave the tight bound on this simple path, but I just want to emphasize this is something that one of the techniques that we use to analyze Markov chains is coupling, where you choose two different things that are just differ by one, and you show that they're more likely, or at least as likely, to get closer together by some Hamming distance or by some area between them, rather than getting farther apart. So it's a pretty straightforward proof to show that you get a polynomial bound. So I took out the slides that explain the proof, but it's just very straightforward. He was very clever in showing that this was a tight bound, so that took a little bit more work. So n cubed log n is the answer here. And you could apply the exact same strategy when you have multiple paths. So I choose this vertex v on one of the paths uniformly. So sweeping from left to right, I drop a vertical, I say which path I'm on, and if it could be inverted, then I invert it with probability 1/2. Okay, so it's exactly the same move on one of these paths. And if I go back to the lozenge tiling picture, okay, so this is the exact same picture I had on the previous slide. I could go back if you need convincing. And really what you could think of here, when I take this valley and turn it into a mountain, I'm adding or removing a single cube from this surface picture, which maybe this will make it easier if I change the, aspect ratio. It's easier to see that on the left I have a cube missing, and on the right that cube is now present, and that's what I'm going to evolve. Okay. All right. So my Markov chain says choose a hexagonal region, and if you see 3 lozenges, rotate it 180 degrees. And that performs this visual trick of adding or removing a cube. Okay? And I have the exact same chain for 3 colorings. So on 3 colorings, I choose a point at random, and I choose one of the 3 colors. And if I can recolor it, I recolor it. Okay, so I chose that red 1, and I chose the color 2, and boom, I changed it to a 2. Okay, and I could go back by the exact same procedure. And this might seem constrained, like what are the chances you have something that's surrounded by, it has to be surrounded by, all of its neighbors have to be one color. But you could convince yourself that this is also connected Okay, you could get from any coloring to any other coloring, and to convince yourself of that, you could, each of them you could move down to the lowest possible coloring. Okay. Okay, so you pick a cell, recolor with, with probably 1/2 if possible is how I described it here, and this is also a mountain valley chain. Okay, so I'm going to just give you, this is, not much here is at all new, so I'm just going to give you a summary of what happens if you evolve these surfaces. So I've described it in 2 and 3 dimensions, and obviously it generalizes to higher dimensions. So for the monotonic path picture, this is the edge disjoint picture, or sorry, the vertex disjoint picture. In 2 dimensions, that's when you have a single path. I said there's a really easy coupling proof, so this is pretty straightforward to show that it mixes quickly. In 3 dimensions, previous work with Luby and Sinclair and following work, actually I should also have work with Prasad Tetali, and then David Wilson's proof gave tighter bounds, show that when you add and remove cubes to this lozenge tiling picture at random, this is also rapidly mixing. In 4 and higher dimensions, there actually are natural applications of this that are kind of cool, and it's still open, okay? And then you could ask the same thing for the coloring picture. So for 3 colorings, this is really easy to see how it generalizes, right? I have an n by n square or an n by n cube and so forth, and I have colors so that neighboring cells are differently colored. So I'm describing the coloring on the dual. In 2 dimensions, the one path is exactly the same for both of these, so we already know that a simple coupling will show this is rapidly mixing. In 3 dimensions, the same work showed that you could get a random 3 coloring of an n by n region. I gave away the punchline. This last line wasn't supposed to be there. 4 we don't know, 5 we don't know, but we do know now that if you're in high enough dimensions and you're doing this simple recoloring, the Markov chain is slow. It actually, somewhere from 3 to, say, 100, there's a change where it goes from being polynomial time to suddenly being exponential time, okay? So if this seems mysterious, I will try to give just a flavor, which is if you're in high enough dimensions, you have a lot of neighbors. And it turns out that if you sampled, what you would see is one of 6 types of configurations. On one of the 2 sublattices, you will see mostly one of the 3 colors, okay? So you might have on the even sublattice mostly blue, and if you do that, then on the odd sublattice, you could have they're all independent, green or red, so you get a lot of different configurations. So even though you're forcing one color to one half of the lattice, you get enough freedom from the other colors that in high enough dimensions, this ends up being the dominant state, and it's hard to move between these 6 different states. Don't worry if that didn't make sense, but for those of you who are wondering why it suddenly becomes slow, that's the picture. Okay, so that's the background for the unweighted case. And you could do the exact same, you could ask these same questions when you add bias, okay? So I'm going to explain what I mean by bias. But the reason that I'm looking at the biased question, I'm going to try to motivate with integer partitions. So going back to the beginning, I'm just reminding you that these are the Ferrer's diagrams. All of these paths have an area, and I'm grouping them together according to the area underneath the curve. And sampling integer partitions is the same as sampling paths with a fixed area underneath, and that's what I'm going to try to do. Okay? So, well, I know how to sample lattice paths. So all of them are equally likely. So if I get one with area n, all of the paths with area n are equally likely. So I do rejection sampling. So you could imagine that I choose one of these lattice paths uniformly. If it has area n underneath, it's a perfectly uniform sample, or close to uniform if I use a Markov chain to sample this path. But I'm sure you see the problem, which is if I sample one of these lattice paths, I stay close to the diagonal. I'm within square root n of the diagonal almost surely the entire way. But I want to get, so I'm going to sample something which is about, has area n squared over 2. So I have to be in an n by n region to include the partition, which is n, or 1, 1, 1, 1, 1, 1, n times. So I'm in an n by n box. I'm going to have things with area which is much too high, right? I'm interested in getting something which has area n, and the probability of seeing that is certainly exponentially small, okay? So the solution is to bias things towards the smaller weighted areas, okay? So this is called Boltzmann sampling, and the Boltzmann distribution from physics, or the Gibbs distribution, says given one of these paths, I'm going to weight it by lambda raised to the area underneath the curve, okay? And I get to choose what lambda is. Okay, so I'm going to guess what lambda is. Later on you'll see I don't really guess, but in principle this is how Boltzmann sampling is done. So the 3 things that you want to achieve is I'm going to consider a family of distributions. Each one of them considers a slightly larger lambda. So lambda is going up by about 1 over n each time. So I have a polynomial number of distributions. And then each one of these I'm sampling so that the distribution is, the stationary distribution will be proportional to lambda to the k, okay, for this particular lambda, where k is the area under the curve for each one. So I want that neighboring distributions are close. I achieve that by having lambda, which just goes up by a little bit, but I have a polynomial number of them. I want that for each value of lambda, sampling is fast, okay? So this is going to be the bias chain that we're going to be talking about. So I want to sample lattice paths, but I want to bias so that the stationary weight is not uniform over all sizes, but is this Boltzmann measure, okay? And third, I want that of these polynomial different distributions that I have as I change lambda, at least one of them has non-trivial weight at n, okay? So I want that if all of them had very small weight, this wouldn't help, but I'm hoping at least one of them will capture and will have its mode or something close to that at n, and then I can use that one to sample, okay? Because so things of size n will come up often enough, and I could use rejection sampling. So that's my strategy, okay? So choosing the lambdas close is easy, but now we have this question of if I have this, this lattice path, can I alter the Markov chain so that my distribution is no longer uniform over paths, but converges to the distribution we're interested in, okay? So this is my time-intensive PowerPoint slide. Preparing it, not explaining, okay? So I have one of these paths, and I'm going to repeat and do the same thing. So I'm going to put down one of these intersecting daggers, and if it's a valley, then I can add the square, which should be coming up. I don't know why it's delayed. Okay, there it is. So I can add it, but I'm going to only add it with probability lambda, which in this case is less than 1. If I choose a peak, I can remove it, and that I do with probability 1, conditioned on choosing that point. So I am adding things at rate lambda and removing them at rate 1, and this is going to bias things towards configurations with smaller area. And if I chose any other point, then I do nothing, and I stay where I am, okay? And so I claim that just very simple probability, if you use detailed balance, you can see that this is going to converge to exactly the distribution I want for the Boltzmann sampling, which is lambda proportional to the area under the curve, and z just normalizes so that this is a probability distribution, okay? And the exact same strategy lets me do bias surfaces in any dimension. And I want to know how fast. So here's the punchline. okay, for the bias chain. There were a series of works that all say the same thing, which is that sampling with any bias is fast, okay? So the first work was Benjamini, Berger, Hoffman, and Mosel in 2005. They were looking at biased card shuffling, was the name of their paper, okay? So remember that these paths come up in nearest neighbor shuffling, nearest neighbor transpositions, and they have a very complicated proof that showed optimal time of n squared. So I want to remind you that Wilson's result for the unweighted path was n cubed log n. So when you add bias, things actually converge faster, which isn't surprising. If you think about a one-dimensional random walk, if it's unbiased, it takes n squared to get to the origin, and if it's biased, it takes linear time. Okay, so the fact that this is faster maybe makes sense. With former students, Sam Greenberg and Amanda Pascoe, we showed the exact same proof in 2 dimensions with a much easier strategy. Okay, both of these are optimal. The n squared is optimal mixing time. And ours, we use, again, this simple coupling, but we use it was kind of funny exponential metric. So we came up with a strategy that lets you do this in a much more straightforward way. And it generalizes to higher dimensions as long as lambda is very large, okay, larger than d squared. And then more recently, there were a couple of results. So David Levin and Yuval Perez showed this for arbitrary lambda, okay? So the first 2 results are when lambda is constant, but the result that we need here is going to be when lambda is, can be 1 over n, okay? So it could scale with n, and they show that the chain is optimally mixing, again, even when lambda is quite small. And finally, Caputo, Martinelli, and Toninelli looked at this problem in 3 dimensions. So they looked at the lozenge tiling picture and looked at biases there and showed that you, again, have rapid mixing. Okay, so that's the series of results. And we're interested, the Levin-Perez is what we need in order to complete this. So what I just said by all of those results that I'm not explaining are, we knew we could get the lambdas that are close. We know that for each one of these distributions, whatever lambda is, we can sample and converge to the weight, this Boltzmann weight for any lambda efficiently, okay? So we just have this last piece, which is, how do I know that at least one of these distributions is going to let me output something of size n with reasonable probability, okay? So again, I want to either go through all of the distributions, because there's just a polynomial number, and or I want to choose one of them. And I'm going to just output paths according to this probability distribution. And if the area under the curve is n, I output it. Otherwise, I reject and I start again. Okay, so I want to do this so that my rejection, that eventually I don't reject something and I will get something with non-trivial probability that has area n. Okay, so summary, this is like the last piece that we have to satisfy. So do we know that at least one of them has this probability? And the answer is yes. And I'm going to show you 2 different reasons that the answer is yes. Okay, so the first method is that pretty recently, DeSalvo and Igor Pak showed that the numbers of partitions of n grows as a log concave function once n is greater than 26. Okay, so Pn is the number of integer partitions of n. And if I take the series Pn, Pn plus 1, and so forth, this is log concave. Okay? In fact, I don't know if they realized this, if you add 2 neighboring ones and you consider the series Pi plus 1, and then the next 2, and then the next 2, that's log concave all the way. So it's not quite log concave at the beginning because you have this oscillation between odd and even numbers, which is just kind of curious. But from their result, you could prove that the other one is, which would have also been enough. So the PK series is log concave, and that means that if I look at the distribution of my Boltzmann sampler, which is pk times lambda to the k, pk plus 1, lambda to the k plus 1, and so forth. So if I look at that bias distribution, that's also log concave. So if you think of it, if I multiply together lambda to the k minus 1 and lambda to the k plus 1, that's equal to lambda to the k squared, right? So if it was log concave before, it remains log concave with these Boltzmann weights. Okay, if it's log concave, the only property that I'm going to use about that is that it's unimodal. Okay, so I'm sampling under a curve, which is peaked somewhere. We want it to be peaked at n, but it's just peaked somewhere. But for each one of these, if the distribution is unimodal and I'm walking back and forth, then I converge in polynomial time. So I'm just throwing out this fact, and that's what we end up using. Okay, so this tells us that there's some lambda. In fact, if we set lambda to the ratio of Pn and Pn plus 1, then if you look at this Boltzmann weight, Pn plus 1 to the times lambda to the n plus 1 is equal to Pn times lambda to the n. So I'm choosing it to be this ratio so that the distribution I'm sampling from is equal at n and n plus 1, and it's unimodal, so we know that n is the mode. Okay, so it's just a very handy trick. So this is sort of the end of the story, but it isn't what our contribution was, so I'm going to go one step farther and just say that this is great when you have it, but it took a lot of work to prove these distributions are log concave. And typically, if you have something, for example, these skew partitions, which I spelled wrong, they're not partitions. If I want to say sample these squares above a certain bottom line, so I don't want to actually go down to the empty one, then this log concave approach doesn't work at all, but the following approach will. Okay, and this does come up. Sometimes people are interested in partitions with certain properties that fall into this kind of family. Okay, so our method, this is work with Matthew Farbach, Pratik Bhakta, and Ben Cousins. We can get it for free by everything I've just told you. So it's just kind of a cool observation. So I want to know that this picture is avoidable. So it could be the case that every single distribution has exponentially small mass at n. So as I change lambda, I never get a sample of size n in polynomial time. Okay, that's the bad thing I'm hoping to avoid. So I'm going to make the following observation. My distributions, as I go through these values of lambda, they're all close. Okay, so the total variation distance between the distribution at lambda I and lambda I plus 1 is at least a half. So there's a lot of overlap of mass. I start off with the mass concentrated all the way to the left of n, and I end up with mass concentrated all the way to the right of n. So there's a continuity argument that says there has to be a distribution so that on that particular distribution, a third of the mass is below n and a third of the mass is above n, at least. Okay? Now, I could still, of course, have no mass at n, right? But that can't happen. And it can't happen because we just proved that for all lambda, this chain is rapidly mixing. Okay? So on this particular distribution that has high mass below n and high mass above n, it has to have non-trivial mass at n, or the chain would not be rapidly mixing. It would be a bad cut that would show that you're going to take exponential time to get from the left to the right, but we know that's not the case. Okay? So it's kind of cool that the proof of fast mixing is what we actually use to analyze each of these distributions and show that they're good for Boltzmann sampling. So very simple observation that I hope you'll remember because so this is the whole story, okay? So there has to be some distribution where you have mass below and above, and the fast mixing tells us that we can sample. Okay, So just because I promised Jeremy that I would give a result from 1978. So this is sort of the story right now, is there are two different approaches. So the classic dynamic programming or generating function, or just the counting approach, which is we can count integer partitions exactly. If you could count exactly, you can use that in order to sample uniformly. So there has been a solution that's been known for a long time that is not based on Markov chains. And if you do this as well as possible, it takes n to the 2.5 space and n to the 2.5 running time. And it also generalizes to skew partitions, but you get a much more complicated thing. So I just wrote polynomial time, okay? There's this incredibly beautiful work that came out around the time that we were working on this Markov chain approach. So our Markov chain beats the runtime of the classic method, and it absolutely obliterates the space. So it takes very little space, because when you're doing a Markov chain, it's memoryless, which is very convenient. So we win big on space, but then we learned of this generating function Boltzmann sampler. They have some fancier name that came out, which is quite beautiful. So it's based on using generating functions when you have a very simple distribution that you're trying to sample, and it's just incredibly fast. So theirs does better, but it won't adapt to these more complicated cases, such as when you have these skew partitions. So it only works when you really have these simple generating functions that are recursive. So just some background there. Okay, and then just for fun, so I'm going to switch over to the third part of my talk in a second, but I just said that we have fast mixing for these biased paths. We also have fast mixing for biased surfaces. I'm cheating a little by these pictures because the Caputo, Martinelli, and Toninelli work holds when the height function on the boundary is flat. It doesn't work for the pictures that I'm about to show you, but we ran it anyway. And this is what lozenge tilings at different heights look like. Okay, so for each one of these, I sampled so that the area, the volume under the curve was preset at different values. And it's quite beautiful that you could sort of, it looks like you're kind of taking MRI slices of some larger thing or something. So they're nice pictures. Okay, so I've told you that we can sample unweighted monotonic surfaces, and then we can sample these biased ones, at least in 2 and 3 dimensions. For the third part of the talk, I'm going to switch to a different generalization of the unweighted 3-coloring case. So remember, 3 colorings are when you have edge disjoint, but not necessarily vertex disjoint paths. And this is a model that comes up a lot. Physicists study it. It has just incredible mathematical properties that I'm not going to say a lot about. But the generalization is called the 6-vertex model. Okay, so I remind you, I'm sorry I'm jumping all over the place. I really put way too much into this talk. So, okay, so we have this path interpretation of 3 colorings, which are paths that are edge disjoint. Now, I'm going to interpret the blue paths, the horizontal ones as arrows to the right, and the vertical ones as arrows up. And by default, where I don't have a blue path, so the black lines are down and left, okay? So I go from this picture of 3 colorings, which hopefully you look at this and immediately see colorings, like I do, and over here, where I'm reinterpreting it now with the arrows as directed paths, okay? So you get these distinct paths, and they go from the bottom left up to the top right. And if you look at this picture, it's an Eulerian orientation. Okay, so I'm ignoring the boundary, but for every internal vertex, you have 2 arrows in and 2 arrows out. Okay, so maybe that's not obvious from anything that I've said so far, but all you have to do is verify all possible blue paths that could come into a given vertex, and you'll see every single one of them is 2 in and 2 out. So the 6 vertex model, it's called 6 because of the 4 choose 2 ways you could have the incoming edges pointing into a given vertex. So locally at each vertex, if I have 2 arrows pointing in, there's 6 possibilities. Okay, here they are. Okay. So the 6 vertex model is going to give each one of these a different weight, W1 to W6. And if I have a configuration, the weight of that configuration is the product measure over all of the vertices of the weight at that vertex. Okay, so this is no longer weighted in the sense of biased surfaces where you're looking at the area underneath. This is something which is talking about the surface area, right? It's saying locally what you have at each vertex, and I'm taking the product of all of those. Okay, so I have 6 weights, which is way too much, but we'll simplify that. And the weight of a configuration is the product of so I summarized it as Wi. It's the product of Wi raised to the number of vertices with type I. Okay? Okay, and then we normalize by z to make this into a probability distribution, so that's just the partition function. So fortunately, so first of all, let me just observe that if all of the Wi's are equal to 1, this is proper 3 colorings. Then every 3 coloring has the same weight, okay? We're going to be interested in what happens elsewhere, and a 6-parameter family is too much for any of us to deal with, but fortunately, there are some invariants that relate the Wi's, okay? So I'm going to go back to the line, the lattice path interpretation. So of these 6, I'm just keeping around the arrows that are to the right or up, okay? So going back to, I'm flipping back and forth between this orientation picture and the lattice path picture. So right now I'm showing it in terms of which edges are present at that vertex, okay? It turns out that even though this is 6 parameters, there are really only 2, okay? So the crossing ones and the empty ones are weight A. The straight segments are weight B, and the turning segments are weight C, okay? So is this just a subset of the possible weights? Well, maybe I could convince you that this captures the entire picture through the following. I could have different weights for 5 and 6, but I'm going to remind you that every time you have a turn up, you also have a turn down, and you alternate. So these 2 numbers are closely related. Well, I'm lying a little bit because your turn up could be type 1, but if it eliminates an up, it also eliminates a down. Okay, so you could keep working this and realize that there are all sorts of constraints that enforce that these things the numbers of each type have to be related, so we can re-weight things. So this is just a change in variables that reduces it to 3 different parameters, and you can make C1 always. So I could renormalize, because remember, the weight of a distribution I'm dividing by the total, so one of these I can get rid of. Or if you want, you could think of it as a 2-parameter family as A over C and B over C. Okay? So 3 weights, crossing and empty is A, straight is B, turning is C. I didn't make up this model. I certainly didn't make up the name, because 6 vertex is ridiculous once you know what it is. Okay. So here's my Markov chain. So remember, my Markov chain says on one of the paths, choose a vertical intercept, and if it's a peak, switch to a valley if you can. Okay? If you can means you won't cause a collision of edges, because you have to stay edge disjoint. So here's a possible move. And if you look at it, oh, I actually have this wrong. I was trying to be clever about the weights. It's not 1 and 1. So locally, This is a corner, a corner, a corner. So this one locally has weight c cubed, and this one has a straight, a corner, and a straight. So this should have weight b squared c. Okay, so my 1, 1 is wrong. I want to go back and forth with those proportional weights so that I converge to the right distribution by detailed balance. I think the other two I got right. Okay, and I do the same thing. For each of these moves, I'm going to do the move so that the probability of going to the right divided by the probability of going left, each one of these is the minimum of 1 and the ratio of the stationary probabilities. So most of my vertices stay the same in the before and after, so those will all cancel, and I just have to look locally where I'm doing the move, and you get something like this. So this is just the metropolis probabilities that from the celebrated metropolis algorithm, and this converges to the right distribution. Okay, and here's another example. So I start off with something which had a C, and then 3 straights and a turn, and I go over there, and I still have, so you just kind of, or you still have an A over here, but now I have more turns, so you get this ratio again. Okay, so these are easy to calculate. So that's the chain I'm going to be analyzing. So it's just, again, a locally weighted chain. You have to look at the vertices right around the square you're changing, but that's it. So we want to know how quickly this chain converges. And the answer is both beautiful and complicated. And this is the picture of the 6-vertex model that has nothing to do with Markov chains. It comes from physics. And this is the conjectured phase diagram for the 6-vertex model. So remember, we reduced it to 3 parameters, and I said you could normalize by C. So we have B over C vertically, we have A over C horizontally, and then I have these funny names. So the configuration is considered ferroelectric. Are these 2 triangles, these infinite triangular regions, that correspond to A greater than B plus C, or B greater than A plus C, okay? So there's symmetry because if you take your oriented picture and rotate it by 90 degrees, you map A to B and B to A. So there's a simple transformation that says this has to be symmetric, okay? So these 2 outer corners are called ferroelectric. This bottom finite triangle is anti-ferroelectric. The middle is considered disordered. This curve, I'm not going to say anything about. It's something where you can calculate something exactly. So there's just some slight curve where things simplify. And then you get this 1 green dot in the middle. So any guesses what the green dot is?
The uniform measure.
Is the uniform measure. So the green dot is what I showed you before, uniform 3 colorings, and we know the Markov chain is fast at that green dot. Okay, so what else do we know? Nothing. Okay, so here's...
Quick question, do these correspond to anything in the physical world?
Well, given their names, yes, but do I know what they are? No. Yeah, they do, and
Okay.
yeah. But it's physics, right? Okay. That wasn't taped, right?
It was.
No, but I just mean that, there's a lot of intuition. They're looking at an infinite model, and they're looking at whether there's unique limiting measures, so uniqueness of the Gibbs state is what they would say. So they're asking different questions. So I said that partially because it's, they're not saying anything about mixing times at all, but I will. So I'm asking the following question. So again, this picture from physics is on the infinite lattice, and I'm asking the question, are there boundary conditions so that the chain takes exponential time? Or is it true that for all boundary conditions, the chain always converges in polynomial time? Okay, so the way you think about three colorings is called free boundary conditions, where I have no constraints. But you could also imagine that I fix the colorings around the boundary and I want to choose uniformly within that, and that's fixed boundary conditions. So I'm giving myself the leeway to play with things like that. So what's proven is that one dot. Okay, I'm going to show you a little bit more today. What's conjectured is that the anti-ferroelectric and the ferroelectric regions, if your parameters are from there, the chain can be slow. And in this disordered region, we believe that the Markov chain is always polynomial time, and that there's sharp transitions at this weird rectangle. Okay, so this is, no physicist would state things this way, but what they believe pretty much implies this for us. Okay, so I think this is completely believable. I really tried hard to prove anything besides that one dot is fast, and so far have not been able to. The methods that I've tried don't generalize. But there has...
For your Markov chain or for some Markov chain?
For my Markov chain.
For your.
Yep. Yeah, so these are not hardness results. This is saying that the local Markov chain, which is changing the color at a single point, that chain is slow or fast. I will say that there are comparison theorems that say that from this you could say any local changes. So if you're changing any little o of n squared part of the region at a time, it will apply to that also. Okay, so it's more general, but it's not a global chain. So a couple of years ago, we started to make progress on the red region. So this is what Liu, this is Jinyi Tsai's student, Liu, showed that this little square in the antiferroelectric region, there are boundary conditions for which the chain is slow. And this is our new result. Okay? So with my student, Matthew Farbach, this 2 days ago got accepted to random, so this really is a fresh result. We showed that for the entire ferroelectric region, all the way up to where you have this phase transition, this whole region can be slow, and we got a good part of the antiferroelectric region. So I have just a few minutes left, but I'm going to give you two totally different arguments in the antiferroelectric and the ferroelectric regions. So let me start. Well, first of all, these are our theorems. So this is not very interesting to read, but it says that for the ferroelectric region, there are boundary conditions, and in the antiferroelectric region, for free boundary conditions in particular. So those values are just describing these three red regions. So that's all the theorem is saying. Okay. Okay, so I'm going to start with the ferroelectric region. And I told you there's a symmetry, so I'm going to focus just on this top triangle. And the top triangle is where B is greater than A plus C, is what characterizes that triangle. So let's go back to what that means in terms of these paths. So it means that B has the largest weight, and B are the ones that go straight. So I'm looking at So I'm looking at paths that the maximal weight is when these things, actually, I think I have this wrong here. Yeah, I'm sorry, I circled this wrong. I'm going to describe it for A greater than B plus C. So my proof, the way I have it in the slides, is going to show that the crossing ones have the most weight, more than the turning and the straight ones, okay? Which is just the bottom corner. Okay, so what I'm going to do is I'm going to start with boundary conditions so that I start with well-separated paths, okay? So each path is going to go straight or turn, but they're going to be well-separated, so I'm not going to get these crossing points very much. And if I evolve this for a long time, each one of these paths is going to stay within its own chamber and not even discover another path. Okay? So it's not quite a uniform random walk. They're now correlated random walks where I'm more likely to go straight than turn, but that actually just compresses the width of my typical path. And then I'm going to come up and show that these paths can come together and have a lot of these crossing, these intersecting points, where I have something with very large weight, okay? So this is what I've drawn. So I have all of my paths start at these well-separated points on the left and on the right. These blue chambers are well separated. So if I walk for an exponential amount of time, each one of these correlated walks stays within its own blue chamber. Okay, so in exponential time, the picture still looks roughly like this, all right? But eventually, in exponential time, I will get something here where it's sort of hard to see that the starting points of these paths are exactly where they are here, but now I've made these things come together. So I have a quadratic number of these intersection points, all right? So the punchline is that my state space is going to look like this. I'm going to have these paths that wiggle for an exponential amount of time and never discover each other, which has high entropy. There's a lot of these. And then I have this many fewer configurations that look something like this, but these have very high energy because each of these are contributing A to all of those intersection points. And so I get a picture that's going to look like this, and that tells me I have slow mixing. Okay? Mm-hmm.
Is your mixing time from the worst initial point? Or
Yes, it's from the worst initial point is how we define, when I said the mixing time, that's right.
So do you need the left side?
I do, because there's enough of those that I can set things up so that the mass is equal on both of them.
But do you need that, or do you just need the right mass?
I need that the middle is exponentially smaller than both sides. Okay? So just quickly, the anti-ferroelectric region is going to be a similar strategy. But here I'm favoring corners. Okay, so my corners have the highest weight, and the straights and intersections have lower weight. Here are what we call the ground states. So there are two configurations with the maximal number of weight C intersections, the odd and the even. Okay, so I'm looking at the upper left point, whether all of those points are odd or whether they're even. And in this sense, if ever you look at the places in the configuration where you have a corner, it forms an independent set. Okay, so these are the two maximal independent sets, the blue dots. So this is the ground states for independent sets. So this is going to behave a lot like weighting independent sets where you favor having more points in your independent set, and we've studied that a lot. So in terms of the Eulerian orientation picture, here are the two different ground states. So the turns exactly correspond to saddle points, and there are two different saddle points where you have in and out, or in and out. Okay? And so here's the picture, is that you're going to have dominantly even, dominantly odd, and then the ones in the middle that are half and half. But when they're half and half, you have to have far fewer of these corners. And so this is the picture you have for independent sets. We actually do something a little bit different, but this is just giving you a flavor of how this goes. So more precisely, if this is a configuration that has a lot of green and a lot of red, the blue lines are bisecting corners that are not saddle points into the green part and the red part. And what I can do is choose one of these blue paths and flip the colors on the other side. So literally, I'm switching the orientation of the arrows to the left of the blue path and not to the right. And I map onto something on the right, which hopefully has now a lot more of these saddle points. Okay? So doing it in a way that the gain is larger than the information it takes to reconstruct where this path was. This is called a Piles argument, and I'm just going to cover the details. But I will tell you, this is exactly the strategy that Liu used. And he said that if C over A and C over B are both less than the self-avoiding walk constant, because this blue line is a self-avoiding walk, then you could arrange it so that when you flip, you go from an A or a B to a C. So you gain C over A or C over B all along the path. And the number of these paths is, that shouldn't be a subscript, that should be mu to the n, okay? So this is the self-avoiding walk constant. The number of self-avoiding walks is something like 2.63 to the n, so you take the best bound on that, and that's how he gets this little square. And all we did is recognize that if you use a generating function to describe the paths, when you have these paths, you alternate A's and B's. So they don't have to both be really small. C over A and C over B don't have to both be small. One could be large as long as the other is even smaller. Okay, so you just work out that, and to do this, we don't count self-avoiding walks, we look at non-backtracking walks, so we just look at things that don't go back the way you came. So that's why his square is a little bit better. Instead of having the side length of the square be 1 over 2.63, we have it as a third, but then we get this entire region. Okay, so my recap, before Jim yells at me, is I showed you 3 different results, 3 different families of results. The unweighted paths, where for 2 and 3 dimensions we know things are fast. The bias chains, where, again, we know that things are fast for the monotonic surfaces in 2 and 3 dimensions. And then this 6 vertex model, we have analyzed all of the ferroelectric and most of the anti-ferroelectric region. And here are my open questions, okay? So we know that the 3 coloring picture in high dimensions takes exponential time to converge. There's a phase transition as you increase dimension. I don't think that's the case for the weighted surfaces, but there's no proof, okay? So we know that things are fast in 2 and 3 dimensions. It's open even in 4 dimensions. We know that when you bias things, they tend to go faster. So we know, we understand this for the monotonic surfaces, but we haven't analyzed this for the height function corresponding to 3 colorings. So 3 colorings in high enough dimensions are slow. What happens if you have the bias chain in high dimensions? Honestly, I really came up with this question last night when I was writing the slides. I really don't know the answer here, but it's interesting to combine the 2. And the last one, I will just point out, we have this solitary point where things are fast in the 6 vertex model, but the entire disordered phase is believed to be quickly mixing. So can we show it for anything larger than a single point? Show me any region where you could prove that, even a line in the disordered region where you could show that the chain is always fast. I haven't been able to do that at all. So this, I think, is a very nice question. So thank you.
Okay, thanks. Let's take a few minutes for questions. Please remember to wait for the microphone to come back to you before you ask your question.
Hi, Dana. Thank you very much for the talk. It was very illuminating. I wasn't sure about asking about it, but the other question were a bit related to this. So many of the techniques is about finding one Markov chain and sometimes a very small subset of boundary conditions to show either that it's converging fast or slow. And but it generalized to a lot of other Markov chains which are local. If someone was, for instance, for the area where you get slow convergence, inventing a new Markov chain which would be non-local,
Sure.
and converge faster, wouldn't it be a problem that the computation, the non-local computation, will take more time? The very trivial example is your first Markov chain was you pick a point. If it's a corner, you flip it. If it's not a corner, well, you don't know anything. And if your boundary condition is just n 0, 0, 0, 0, 0, 0, then you will have a linear number of those. It looks very inefficient. But a non-local one would pick an edge and look for a thing to flip, and it will take time n anyway. So isn't there? So is there really a hope to find better Markov chain non-local? I think not, but you're the expert.
No, absolutely there are. And you know, I've been working in this area of trying to understand these phase transitions, these diagrams. When you show that something is slow, in my opinion, there are two reasons to do that. One is just phenomenological, to really say this is inherent in the physics model and it's explaining something about the physics. But the other is to say, wow, local chains, which are the first thing you would think of, really are not good here. Let's use something else. So there are all sorts of cases where you do a transformation of the state space into a different world, and there you could sample more easily, which of course you can map back. So the icing model is a good example. And at any temperature, including where we know local chains are slow. Or you could do what's called simulated tempering, which is like annealing, which is changing the parameters as you go along. So there are lots of things that if you're interested in sampling, which is only part of what I'm interested in, I'm also interested in these natural local chains, you know, there definitely are reasons to look at any method. And I showed you before that generating functions are even more efficient for sampling certain things. So of course, if you want to sample, use anything. Sure. So.
Okay, other questions?
Okay.
So if I get it right, the dotted circle that you have, let us call it free fermion line or a diamond model line.
Yes.
And you say that you don't have fast mixing even on that line.
Well, for this local Markov chain. So on that line, remember when I showed you the phase diagram, I said there's a dotted curve, ignore it, because I stole the picture from someone else and didn't want to talk about it. But you can calculate things exactly. So there are methods where you can sample efficiently, but not with this local Markov chain. We don't know that or any quasi-local Markov chain will sample there. So I believe the disordered region is completely open in terms of mixing rates of these types of local mountain valley chains or anything quasi-local, which just changes some little o of n squared part of the state space at a time. And yeah, so including that, where you can calculate you can sample by other means. Yes. Mm-hmm.
Other questions? I have one. Oh, okay.
I just want to see you run.
Hold on.
So, in the first model, there is a phase transition, right? And what you know is that
The
when
first model,
the first one, the first part of the talk, at the end you show us that for the true and free,
colorings, if you go to high enough to this one?
Yeah.
Yeah.
Do you know something about the phase transition? Is sharp, is smooth?
Oh, we know nothing about the phase transition because to study a phase transition, you need a continuous change, and I'm changing the dimension.
Yeah.
So, but the reason it should be true is that if you look at independent sets in higher dimensions, the phase transition decreases. The critical point in higher dimensions goes down. Where it's crossing 1 is presumably where we're getting our results. So there is sort of a continuous way of looking at this, but the coloring model doesn't at all. All we could prove, and I'm sure our bounds are not at all tight, there were 2 independent results. One was with, I did with Galvin, Kahn, and Sorkin, and independently Ron Pellet came up with the same proof pretty much, independently, and it just shows that for some really large dimension, you can show that you get this, this kind of bad cut, okay? I mean, really, the results also apply to uniqueness of the Gibbs state, which shows a phase transition in physics, and there's nothing tight at all. So, but yeah, it's sort of suggested by weighted independent sets, is all I can say.
Okay, to keep us close to schedule, I'll take the chairman's prerogative to ask the last question, which is, so for weighted permutations, you and some of your students have done a nice job of proving rapid mixing in certain cases that of a conjecture that I had about fastest relaxation time. I'm wondering, is the same story maybe true in this case? That is, in the disordered region, where there's a conjecture that it's always rapidly mixing, might it be that the slowest of those cases is actually the green dot?
Oh, absolutely, that could, yeah, absolutely.
That's likely to be the
completely
case, yeah.
reasonable, which is the...
So it's a highly frustrating situation, right? To have the
I
what you
don't
think is
know
the
that
worst
that's-
case, the only one that you can handle, right?
Actually, I have no
I mean,
evidence that
I
would be
know
the
that
worst.
pain, right, myself.
Yeah.
Yeah.
I mean, in your case, I understand why you would think it's the worst. Here, when you're biasing corners, straights, I'm not sure.
Okay, it might be, but it might not be. Yeah.
But I think that morally it's true.
Right. Okay, that's
Yeah.
it for this session. There's a coffee break until 11. We'll resume then.